So in this video, we're going to be carrying on with our discussion on dielectrics following on from last video, and we're going to be having a look at concepts such as polarisability, the Clausius-Mossotti relation, and polar molecules and ferroelectrics. Just a disclaimer, if you haven't seen the previous video, I highly recommend watching that and making sure that you guys are comfortable with some of those concepts, as this is going to be some really quite advanced stuff, and it's stuff that's not typically covered until higher university level physics. So with that disclaimer aside, let's jump right into it. So in our last video, we were talking about the macroscopic manifestation of what happens when you apply an external electric field to a dielectric material. So in here in green is our dielectric medium, and we said that this dielectric medium is comprised of lots of dipoles right here. So for dipoles, I'm just going to simply represent this as a positive charge on one end and a negative charge on the other end. And what was happening is that the electric field was polarizing the dipoles all to orient in the same direction. And what this did was to produce a macroscopic response, which we said was the polarization capital P. And this was given by the number of dipoles per unit volume multiplied by the individual dipole moment of each individual dipole right there. So this is what kind of was happening, and we said that the electric field within the dielectric actually changed as a result of this macroscopic polarization field. But there were a few things in this analysis that we didn't quite go into. One of these things was what was actually happening to the dipoles on a more molecular level, because it actually gets quite complicated. And what we're going to do is we're going to start off by talking about a thing called the polarisability. So say we have one dipole right here. This is just a single dipole. We're going to consider a single dipole with a positive charge and a negative charge. And this dipole will of course possess a dipole moment given by capital P equal to the charge multiplied by the distance. And remember, the direction of the dipole moment is oriented from negative to positive right here. So far, so good. And then I apply my electric field, say it's in this direction right here. And of course, what's going to happen is that dipole will of course orient itself. So as the negative end will face the positive direction of the electric field, and the positive end of the dipole will orient towards the negative part of the electric field. Right there. And the extent to which a dipole will do this is called the polarisability. So it's basically how much of a dipole moment will you get from an applied electric field. And what you find is that the induced dipole moment is proportional to the electric field. So remember, this is lowercase p. The dipole moment is proportional to the electric field. And the extent to which it's proportional to is quantified by alpha, which is called the polarisability right here. So it's basically saying that the induced dipole moment is directly proportional to the electric field applied, and the extent to which it causes a dipole moment for a given electric field is called the polarisability, alpha, right there. So this could be for a permanent dipole like this, or one which wasn't a dipole before, so it had a negative charge like that. The atoms had a negative cloud and the positive nucleus in the centre, and of course once an electric field's applied, this positive charge in the centre would distort, slightly difficult to draw, causing a dipole moment right there. So the extent of how big a dipole moment you get for an electric field is called the polarisability. So that is all well and good for a single dipole. However, within a big dielectric medium, we have many of these guys. We have loads of dipoles all across a surface, and they're all causing a net field as induced by the electric field right there. So we have a big plethora of dipoles all causing a buildup of an electric field, which is the polarization. So to be more accurate, what we actually say is that the induced dipole moment is equal to the polarisability multiplied by the local electric field that a dipole experiences. So this is going to be E local. And of course, by the time you get to a different dipole, you actually find that the electric field changes. So it's only dependent on the electric field that's within the very close vicinity of the dipole, right there. And that's obviously not very useful because we know the value of this big electric field that we're applying. And heck, we even know the value of the electric field within the dipole because we derived that last time. But this isn't necessarily the local electric field that's being experienced at any given point within the dipole, because of course that's going to change depending on whereabouts you are in relation to a dipole. Obviously the electric field is going to be stronger here than it is in between. So this is going to get really, really messy. And in order to calculate how much of an induced dipole moment you get for an externally applied electric field, you have to do some quite clever calculations. So that is the problem that we have right here, is that this relationship only works for a local electric field. It doesn't work for this globally, macroscopically applied electric field at all. So what I'm going to do is I'm going to put this problem to one side, and I'm going to go into a little bit of a detour and talk a little bit about what the polarization actually physically represents. And what I'm going to do is I'm going to consider, again, my slab of dielectric material right here. And I'm going to draw the dipoles that are at the very edge of this dielectric. So there's obviously going to be one dipole that's going to be on the very borderline of the boundary of this dielectric medium. So beyond here is just air or vacuum or something that's not dielectric. And in here we have our dielectric. So let's apply our external electric field right here. And let's think about what are the charges that are going to be on each surface of the dielectric. So on this surface right here, we're going to see that all of the negative charges, because of course the electric field runs from positive to negative, we're going to see that all the negative charges are all going to be attracted to the positive side. So therefore, the negative ends of the dipole are all going to be on the left right here. And the opposite is going to be true of the positive sides of the dipole. The positive charge is going to orient itself towards the negative end of the electric field. So at the surface, we can see that this bit right here is going to have a positive charge, and this bit is going to have a negative charge. And what I want to do is I want to ask the question of what is this charge that's experienced at the edge of the surface right here? How are we going to work out what this charge is? So to do that, we need to know how many dipoles are at this surface of the dielectric right here. So of course we have, because it's a 3D dielectric, we're going to consider this surface right here. We need to know the number of dipoles that are contributing to the charge on the surface, and then we need to multiply that by the charge of each dipole. So let's just go ahead and write that. So the total charge at this surface right here, we're only considering this surface right here, is equal to the number of dipoles that are at the surface multiplied by the charge of each dipole, little q. Now what I'm going to do is I'm going to multiply this equation right here, top and bottom, by volume. Now this might seem a little bit weird, but you guys will hopefully see why I'm doing this in a bit. So I'm going to first of all divide this term by volume, and I'm going to multiply it again because I've just divided it by volume. I'm going to then multiply it by volume yet again. So I've done no harm to this equation whatsoever. This is still the total charge on this surface. I've just multiplied top and bottom by volume. So why have I done this? Well, we can see that this term right here, the number of dipoles divided by volume, this is the dipole density that I was talking about in the previous video, that I just given the symbol capital N right here, so which is technically a density. Its units are per meter cubed, and it's the number of dipoles per cubic meter. So we can therefore substitute in just this N right here, multiplied by Q, multiplied by this other volume term right here. But we're only considering dipoles at the surface of this charge. So what we're only going to do is we're only going to think about a single layer of dipoles right here. This is all we're interested in, because these are the only dipoles that are contributing to the charge on the surface. So what we need to do is we need to evaluate the volume that's actually contributing to the charge of the surface. So there is a certain volume of space that the dipoles are taking up so as to contribute to the charge on the surface right here. So what is this volume? Well, the volume is just the area times the distance. So we're going to get the dipole density times the charge per dipole multiplied by this area right here. And then you've got to multiply by the length of a single dipole, d, right there. But what is Q times d? Q times d is simply the dipole moment P right there. This is what we've said in many previous videos. So we can just go ahead and substitute in for QD P. So this will be the dipole density multiplied by the area of the surface multiplied by each dipole moment. And what I'm now going to do is I'm going to define sigma. And what this is the charge density, the area charge density right there. It's the charge per unit area. So if you divide a charge by the amount of area, then you get the charge density. So it's the charge per square meter, if you like. And so what this is, if we just divide this by area, this is going to be N multiplied by P, the dipole moment. But what is NP? NP is simply equal to the polarization, capital P, right here. This is what we've said in previous videos. We've said that the dipole density multiplied by the dipole moment is just the polarization, the macroscopic polarization. So what we've shown is that the charge density is nothing more than the polarization right here, the macroscopic polarization. So this term right here is just telling you how charged a surface, a cross-sectional surface of a dielectric is right there. That is all that the polarization is physically telling you. However, the surface charge is a scalar right here, and the polarization is, of course, a vector quantity. And of course, not all of the surfaces on this dielectric will be equally charged. For example, if we take this side right here, then hopefully you guys can see that it will be the exact same surface charge density as this surface right here, but it will be negatively charged rather than positively charged. So in fact, the charge density, the area charge density, actually depends on the direction as well. So to be technically correct, you actually write that the surface charge density is equal to the polarization dotted with the normal vector n hat. And the normal vector is the vector that's pointing perpendicular to the plane of the surface. So if your surface is like this, then the normal vector is in this direction right here. And that is going to be a really useful relationship. And that is going to be a really useful relationship right there. So let's go ahead and return to our discussion about how to account for the fields inside a dielectric that are produced by all the other dipoles around one dipole that we're considering. And what we really want to get is we want to get the dipole moment being directly proportional to the external electric field applied. So we really want to get this polarisability alpha as being a constant and being something that we know how to calculate. So how are we going to do this? Well, there is in fact a very clever trick in order to work out how to do this. And to show you guys what this trick is, I'm gonna yet again draw out a dielectric right here. So this is our big slab of dielectric. So it's gonna have lots of dipoles at the surface right there. But what I'm gonna do is I'm gonna cut a hole out of this dielectric kind of in the middle right here. So there's going to be a hole that I'm now going to cut out. It's going to be a spherical hole, and I am going to consider what the electric field is in the center of this spherical hole right here. Now you're probably wondering, why am I doing that? Why on earth am I cutting out a hole in the middle of a dielectric? How is that going to help us at all? Well, the point of cutting out this hole is we want to get a surface right here that's big enough to cause a surface charge density sigma as a result of all the dipoles accumulating on the surface. Because of course we said earlier that sigma is equal to P dot N. And so we want to have a surface that is going to have a charge on it that's caused by dipoles. So this sphere right here needs to be a lot larger than this distance of the dipole right here, this little lowercase d right here. However, we don't want this sphere to be too big, because if it's too big, then obviously that's going to interfere with the macroscopic polarization felt across here, and that's going to affect the surface charge density of the edges of the dipole right here. So we're going to cut out a sphere that's sort of medium-sized, that's big compared to the size of a dipole, but small compared to the size of a dielectric. And the reason we're doing that is because we want to find out what the electric field, this is often referred to as the depolarizing field, is within this spherical cavity, within the dielectric. So inside this hole, just to reiterate, the permittivity epsilon, the general permittivity, is the permittivity of free space. But within this dielectric, you just simply have permittivity epsilon because that's caused by dipoles. So let's go ahead and take our spherical cavity right here, and let's go ahead and think about what is the charge on the surface of this cavity, because of course we want to try and see if we can get the charge density sigma right here. So what is the charge? Well, our electric field, our externally applied electric field, is pointing that way. So this means that there is going to be a giant positive charge that's outside the dielectric over here, and a giant negative charge that's over here. So let's go ahead and colour that in. We have our positive charge out the front right here. This is all outside the dielectric, and our negative charge over here. But what effect would this have on the dielectric? Well, we said that actually all the negative charge of the dielectric would go over to this side because it's attracted to the positive, and all the positive charge of the dielectric would try and get itself over to this side right here. So the dielectric would become polarized in the opposite direction of the electric field. But what about this spherical cavity? What is that going to look like? Well, if all the negative charge within the dielectric is being pushed that way, then that would actually leave this side of the sphere a slight positive charge. So on the surface of this side of the sphere, it would be positively charged, but on the surface of this side of the sphere, it would be negatively charged. And that's simply the reverse of the direction of the dielectric, because of course we have a hole right here. And kind of at the extremities of the sphere, so like the two poles, you're actually going to find there is no charge whatsoever. So it's actually going to be completely neutral right here, but it's going to be at a maximum at this point and a minimum at this point right here. So how are we going to get the electric field then? With differing charges all across the sphere, this is looking like a really, really complicated calculation to do. And the trick to doing this is to consider each point along the surface of the sphere as a little point charge. And of course we know the formula for a point charge. It's E equals Q over 4 pi epsilon 0 r squared. So that's the formula for a point charge. But of course we have loads and loads and loads of point charges all across the surface of this of this cavity. So what I'm going to do is I'm going to take a differential of this formula right here and say that a little bit of the electric field, a tiny little contribution, is each going to come from a tiny part of the charge along the surface, divided by 4 pi epsilon 0 r squared right here. So dq right here is simply the charge of one tiny little point across the surface, and that's going to give a contribution of dE right here. And to get the total electric field within the center of this cavity, then we have to integrate over all of the electric fields. But the total electric field is actually only in this direction right here. This formula over here is in spherical coordinates, and it's assuming that the electric field is pointed radially outwards because, of course, E is a vector, and this formula right here is in the r hat direction, in the radial direction outwards from the center. But of course, this isn't the case. In this case right here, we only have a horizontal component to the electric field because, of course, the electric field lines are pointing from negative to positive, and so therefore you're only going to get a horizontal component of the electric field. So if we say that the z direction right here, this is the z direction it's normally taken to be, is the direction of the electric field, then what we need to do is we need to add a factor which is going to compensate for the fact that it's only in that direction. And if you take the dot product between r hat and z hat, you get cos theta, because remember the dot product is about the overlap and how much of one vector is overlapping in the direction of another vector. And so you get this factor cosine of theta right here, where theta is the angle between the horizontal and any direction radially outwards right here. So we need to actually add a factor of cos theta to this formula right here, because we are only considering the z component of the electric field, because of course there is only a z component of the electric field right here. Now I said that the surface charge density sigma is equal to the charge divided by the area. And if we take this as a differential form, we can also say that it's equal to dq by ds right here. So that is it in the differential form. And so therefore we can express dq in this equation right here as being equal to sigma times ds right here. So let's go ahead and rewrite what our electric field is, our infinitesimal electric field is. That's going to be equal to sigma ds times cos theta divided by 4 pi epsilon naught r squared. But we said that sigma is simply equal to p, the polarization, the macroscopic polarization, dotted with n hat, the normal vector right here. And again, with the dot product, if you have two vectors that are multiplied that are not necessarily in the same direction, then you can simply express this as p times the cosine of theta yet again, because of course you have two vectors that aren't necessarily in the same direction, and the factor by which you have to reduce it, given they're not in the same direction, is cosine theta yet again. So we can substitute this back in right again. So we're going to get that instead of sigma, we're going to get p cos theta times another cos theta times ds, all divided by 4 pi epsilon naught r squared right here. So let's just go ahead and expand out some of these terms and simplify. So we're going to get our constants are p divided by 4 pi epsilon 0, and we're going to get a cosine squared of theta, and ds for a spherical surface, as we said in many videos before, is r squared sine theta d theta d phi right here. And of course there is another factor of 1 over r squared right there. So as we can see, the r squareds are simply going to cancel out yet again, like they often do. And so we're going to get that dE, our infinitesimal electric field, our singular contribution, is going to be equal to P divided by 4 pi epsilon naught cosine squared theta sine theta d theta d phi right here. And now we're finally ready to integrate this over the entire surface. So we're going to get that the total electric field is equal to the integral over all of the infinitesimal electric fields. And that is going to be equal to this right here, integrated over theta and phi. So over the entire surface of the sphere. So let's go ahead and do that. So we're going to get our constants out the front, P over 4 pi epsilon naught, and we're going to get a double integral over theta and phi of cos squared theta sine theta d theta d phi. Now, of course, the phi bit, as is often the case, is quite easy because, of course, there is no phi dependence within this integral. And when you do the integral over 0 to 2 pi, which is the entire domain of phi, you just simply get 2 pi right here. So we just, in fact, multiply this by 2 pi and then get rid of the phi component of the integral. So we're going to get P over 4 pi epsilon naught multiplied by 2 pi. And now we've only got an integral over theta. And of course, the limits of theta are going to be between 0 and pi right here. So we've got cos squared theta sine theta d theta. And of course, you can see that the pi's cancel and 2 divided by 4 is just simply going to be 2 right here. So let's go ahead and see if we can try and integrate this function right here. And this is one of these functions where you have to do a clever substitution, annoyingly. But it's one that's fairly common, and it's probably one that hopefully you guys would have had a little bit of practice at doing earlier on, either in upper secondary school or in lower university. So the way in which you do this integral is you let you do a u substitution, you let u equal cos of theta right here, and then you take a differential du d theta, and that is of course equal to minus sine theta. And then you can rearrange this right here to give that minus du is equal to sine theta d theta right here. And now what you can do is you can write this entire integral in terms of u rather than theta. So we're going to get E is equal to P over 2 epsilon naught. And of course, the limits have to change because, of course, we're changing variables. So this lower limit is, of course, in terms of theta. When theta equals 0, cos theta is 1. Therefore, U is going to be 1. And at this limit right here, you're going to get that when theta is equal to pi, then cos of pi is minus 1. So this top limit will be minus 1. And of course, cos theta we said is u, therefore cos squared theta is equal to u squared. And sine theta d theta is equal to minus du. So we're going to get a factor of minus 1 out the front. But this sine theta d theta is simply going to be du right here. So this is looking like a fairly straightforward integral, though I do want to make a couple of tricksy changes right here just before we do the integral. We can in fact reverse the direction of the limits by multiplying by minus 1. So p over 2 epsilon naught, this is going to be equal to p over 2 epsilon naught times the integral, only this time it's going to be between minus 1 and 1, and we're going to get u squared du. So I've simply reversed the integral by reversing the limits and thus multiplying by minus 1, therefore getting rid of this minus sign right here. But I can do a little bit more simplification because what we have here is a symmetric integrand. U squared is a symmetric function. And what we can do is if we have a symmetric function, and that is a function where if you flip it in the y-axis, it will be exactly the same. it will give the same result, is we can actually double this integral and change the limits to being between 0 and 1 rather than -1 and 1, because we're essentially counting the same thing twice. So if you guys are a bit unfamiliar with these integral tricks, then I do recommend doing a little bit more maths revision. But what we're going to do is we're going to do p over epsilon naught. And this time I've doubled the integral, so it's going to be between 0 and 1 times u squared du. And there we go. We've done a whole bunch of simplifications. So this is going to be p over epsilon naught. And integrating this, we're going to get 1/3 u cubed. And this is going to be evaluated between 0 and 1 right here. And hopefully you guys can see that this is just simply going to reduce to p divided by 3 epsilon 0. So there we go. We have our result. We have that the electric field within the spherical cavity that we defined. So here's our spherical cavity. The total electric field within the center of this cavity is simply the polarization right here divided by 3. So it's 1/3 of the total polarization, obviously dividing again by epsilon naught just to keep the dimensions constant. So the depolarizing field, E, caused by the surface of a sphere is simply equal to P, the polarization, divided by 3 epsilon 0 right there. So now that we've done all this hard work, we're now going to go ahead and write our polarisability formula right here. P is equal to alpha times E, but it's only the local electric field right here. And remember, this isn't the total electric field in the center. This is only the electric field that's caused by a depolarization of this spherical cavity right here. But there's going to be some other contributions as well. So what contributions are we going to have to this local electric field within the dielectric right here? Well, we're going to have our external field right here. So this is the field completely ignorant of any kind of dielectric right here. This is just the field that we happen to apply. But we're going to get our minus P over epsilon naught, because this is, of course, the electric field that's caused by the dielectric being induced. So this is the first depolarizing field. But we've got this additional depolarizing field that's, of course, caused by the spherical cavity. So we're going to be adding P divided by 3 epsilon naught right here. So that's our total electric field at this point in the center, caused by all the other stuff as well as the depolarization field from the sphere. Now, it was in the last video that I actually said that these two contributions are actually the net electric field within the dielectric. So this is the external electric field, and this is the polarization that is in response to that external electric field. Because of course we said that D is equal to epsilon naught E plus P. This is our D term, if you like. That's the one that would be just completely ignoring any material. And this, of course, is our material polarization right here. So I'm just going to go ahead and write E, instead of EX minus P over epsilon naught, I'm going to just write E, which is the net electric field. And we're going to be plussing P divided by 3 epsilon naught right here. So that is our dipole moment right there, expressed as a function of the electric field, which would be the electric field measured in the absence of a spherical cavity. But of course you have the spherical cavity right here as well to have to account for. So let's go ahead and multiply out this bracket. So I'm going to get alpha times E plus alpha times P divided by 3 epsilon naught. But of course we said that the macroscopic polarization P is simply equal to the dipole density, N, the number of dipoles per unit volume, multiplied by the dipole moment P, right there. So what I'm going to do is I'm going to multiply this whole equation by N in order to get the polarization, the big macroscopic polarization P. So this is going to be N alpha E plus N alpha P divided by 3 epsilon 0. right here. And now I'm going to rearrange to make E the leading term. So we're going to get N alpha E is equal to P, capital P, minus N alpha over 3 epsilon naught times macroscopic polarization yet again. I can now factor out a factor of polarization. So this is going to be equal to P, 1 minus N alpha divided by 3 epsilon 0 right here. This is N alpha E. And now I can divide both sides by this fraction, right, by this term right here. So I can get that P is equal to N alpha divided by 1 minus N alpha divided by 3 epsilon naught multiplied by the electric field. But what did I say in a previous video? I said for any material, the polarization is directly proportional to the electric field applied. The macroscopic polarization is experimentally been found to be proportional to the externally applied to the electric field, the net electric field. And I said that the constant of proportionality is simply chi, the electric susceptibility. And so what we said was that P is equal to the electric susceptibility multiplied by the electric field, as long as it's a isotropic material, which in this case we are considering an isotropic material. But we of course have to multiply by epsilon naught just to keep the dimensions constant. So we can see that we have a constant of proportionality here between P and E, and we have a constant of proportionality here between P and E. So therefore we can see that these two are just equivalent. So we get epsilon naught times chi E is equal to N alpha divided by 1 minus N alpha over 3 epsilon naught, because of course it's the same number, must be proportional between P and E. So now all I'm going to do is I'm going to rearrange to make alpha the subject right here. So we're going to multiply both top and bottom by the denominator. So we're going to get epsilon naught chi E multiplied by 1 minus N alpha over 3 epsilon naught, and that is equal to N alpha. So multiplying out the bracket, epsilon naught chi E minus epsilon naught chi E N alpha divided by 3 epsilon naught is equal to N alpha. The epsilon naughts will go on this fraction right here. So let's go ahead and put all the terms with alpha on one side. So we're going to get N alpha plus N alpha chi E divided by 3 is equal to epsilon naught chi E right there. And then grouping these terms right here, N alpha 1 plus chi divided by 3 is equal to epsilon naught chi E. And so rearranging to give alpha the subject, alpha is equal to epsilon naught chi E divided by N 1 plus chi E divided by 3. And what I'm now going to do is I'm just going to multiply both the numerator and denominator by 3 just to make it the same. So we're going to get 3 epsilon naught divided by N, and I'm going to put the 3 within the fraction. So I haven't finished writing this out yet. So there's going to be a chi E on the top, and I'm going to multiply this bracket by 3 because that's in the denominator, and I'm multiplying top and bottom by 3. So this is going to be 3 plus chi E. And this right here, after all that long, hard and painstaking work, is the Clausius-Mossotti relation. This is what we've been after the entire time, a relationship between the polarisability and the susceptibility, which is the experimental constant between polarization and electric field. And more commonly, you'll see it written rather in terms of the susceptibility, you will actually see it being written in terms of the relative permittivity epsilon r, right there. And of course I said that the relative permittivity is simply equal to 1 plus the electric susceptibility. So if you're not familiar with this, then we did all this in the previous video, but hopefully you guys are. So all we need to do is add 1 to this term and this term to write it in terms of the permittivity. So we're going to get, instead of chi e, we're going to get epsilon r minus 1. And then we're going to get this is divided by epsilon r plus 2. And this is probably the more common form that you'll see it being written in. You'll more commonly see it being written in terms of relative permittivity than you will in terms of susceptibility. But either way, it's the same thing. And this is what's known as the Clausius-Mossotti relationship. So there we go. After all this long, hard work, we finally got there. But let's go ahead and see what happens in various instances of concentrations of dipoles right here. So, of course, I said that P, the polarization, is equal to N alpha divided by 1 minus N alpha over 3 epsilon naught. And this was proportional to E. So we had this form of the equation a little further up right here. Here it is. And so we're going to be using this form just to figure out some of the physics of the system and what happens at varying different concentrations. So what is going to happen when N, the concentration of dipoles, is really, really small? And what is going to happen to the relationship between P and E right here? Well, if N is really small, then it follows that N alpha is also really small, because if you have a really small number multiplied by a number that isn't changing, then that's going to give a really, really small number as well. And so if you compare N alpha to this 3 epsilon naught right here, you're going to find that N alpha is way, way, way less than 3 epsilon naught right here. And when you have a really small number divided by a really large number, then you're going to get a number that is really, really close to 0. So if you say you have 0.0001 divided by a number that's much bigger, like 10, you're going to get a number that's really, really tiny. So this term right here, N alpha over 3 epsilon naught, will in fact become completely negligible. And so you can approximate this equation as being P is equal to N alpha divided by 1 minus, well, basically 0. So this is going to be N alpha divided by 1, which is just N alpha. And this is going to be proportional to the electric field right there. So for really small concentrations, for really, really, really tiny concentrations of dipoles, then you're simply going to get that the polarization is N alpha times E. Now, if we remember what we had before, that the dipole moment, lowercase p this time, is equal to alpha E, and P, capital P, is equal to dipole concentration times P, then you can see that if you combine these two, then you'll get this relation right here. But this, it's important to remember, this only holds when you don't have any depolarizing fields, when you don't have large concentrations of dipole that are all kind of forming together in order to create a depolarizing field. So you can't actually just use these two equations and just combine them in most instances. However, in this case right here, because the dipoles are so far apart, they're not creating any kind of depolarizing field. They're just not close enough together to create a macroscopic depolarizing field so as to be felt by each dipole. So this is for really small concentrations. Now for big concentrations, you actually have a really interesting thing. And I'm not going to go into the maths with it, but I'll just introduce what happens at big concentrations. So what you'll find is that if N alpha gets really big, it will actually tend towards 3 epsilon 0 right here. You actually can't get any higher than 3 epsilon naught, but this is what will happen for really large concentrations. You'll actually find that this term, N alpha, tends towards 3 epsilon 0. And what this actually entails is a phase transition where the material, the dielectric material, in fact changes state. It in fact becomes ferroelectric. It goes into a ferroelectric state. And what that basically means is that a slab of material in fact possesses a permanent dipole moment, rather like a magnet, except it's a positive electric charge on this side and a negative electric charge on this side. And the key thing is that that polarization will not disappear as soon as you switch off the external electric field. So this ferroelectric material will possess a polarization even despite not having an electric field there. And this is basically the same as ferromagnetism. So like within iron or cobalt or nickel, these materials are ferromagnetic. They possess a magnetic field even in the absence of an externally applied one. They actually retain a magnetization. And this is exactly the same, only for electricity. So I hope that was really helpful. I know that was a really, really long and complicated video, but I do hope that you guys managed to follow along with all of that. If you have any questions, do comment on the video. I'll try my very best to explain all of this as clearly as I can. But otherwise, yeah, hope that was really helpful, and I'll see you guys in the next video.